Yeah.
I'm sharing my screen.
Yeah, could you test your sharing? Okay, I can see. Yeah, good.
Great.
So thank you very much for joining us. Yeah.
Oh, yeah, thanks for inviting me. I guess it's pretty late, I guess, for you.
Yeah.
Yeah, so
But
I'm
it's
impressed.
okay.
Yeah, thanks for arranging the time zones. But
So are you in your office now?
no, I'm at home.
Yeah.
So no, I haven't seen my office in a year.
Yeah. So
yeah, no, I'm at home.
The situation with the COVID-19 is so bad in
around
Boston.
Yeah, I mean, I live in a small town, Amherst, so it's okay around here, but still, like, yeah, I'm not.
I see. So the situation in Japan is not so bad, but
yeah,
so
the US has been pretty bad at this. Yeah, it's.
Okay, so shall we start the final talk of this conference? The speaker is Romain Vasseur from Massachusetts University, and now he is going to tell us about entanglement transitions in random tensor networks and monitored quantum circuits. So please.
Yeah, so first of all, let me thank the organizers for inviting me here and for organizing this very nice workshop. So I'm the very last talk of this workshop, and I'm aware that it's pretty late in Japan. So hopefully, I will manage to distract you and to make this interesting. So this story is a bit, I guess, different from many talks in this workshop, but there will be some common themes. So I'm going to talk about entanglement phase transitions. And so I'll define what those are, but in a nutshell, there will be phase transitions in the usual sense, but where entanglement plays a key role. Okay, and so I'll give examples where in random tensor networks and in some quantum circuits with measurements. And again, there'll be some, I think, common themes, at least with many other talks in this conference. There'll be some conformal field theories and some replicatrix, but in a way a bit different than other talks. So before I start, let me thank my collaborators on this. So this is some work with Andrew Potter, Yizhuang Yu, and Andreas Ludwig in particular. And more recently, I've been working with people in my group, Braden Ware, my postdoc, and Javier Lopez, a student, and Xiaoming Jian, who's now in Cornell. Okay. All right. So again, since I feel I'm maybe a little bit of an outsider here, let me have at least just have two broad introduction slides just to put this talk in perspective, at least from me, of what I find interesting here and what my motivations are. Okay, so my broad motivation, which has nothing to do with entanglement or quantum information, is to try to find universal phenomena in some regime where you would not expect them at high energy in quantum systems and far from equilibrium in some way. Okay, so universality at high energy or high temperature is a bit counterintuitive, right? So usually when you learn of universality, it's when you take a course on the renormalization group on phase transitions, you learn about scaling laws, and you learn that interesting universal phenomena happen at low energy, low temperature, and long distances, right? And so this in quantum matter theory, the typical phase diagram that people like to have in mind is something like this, where you have a system at maybe at zero temperature, it has a phase transition, a quantum phase transition that's driven by a parameter I call G. Okay, that's driven by quantum fluctuations, and you have a quantum critical point, and you may have very interesting universal physics there. And it separates an ordered state. I don't know, it could be an antiferromagnet, whatever you want, and a disordered state could be a topological phase. I don't really care here. And if you go to finite temperature, then okay, you can have a classical thermal phase transition driven by thermal fluctuations if you're in high enough dimension. But if you go to very, typically the quantum critical point will broaden into some quantum critical crossover. And if you go to very high energy, right, on that scale, the common theme, the common knowledge would tell you, okay, this is going to be a very classical regime, so there's not much quantum mechanics there. And also there's no hope for something universal in the sense of being material independent and so on occurring here. And then so in some way, the transitions I'm going to talk about today, they occur, at least in my mind, in this high energy regime, okay? And so the perspective here that I have, again, still from the quantum matter perspective, is to think of the dynamics of isolated systems, which I think is still something that's also shared by this audience, to think of isolated systems and their dynamics. And so now in quantum matter physics or homophysics, it's not just a theory idea, and it's something that's motivated by many experimental setups. I'm quoting a few here: ultra atoms, trapped ions, NV centers, superconducting qubits. The only feature that matters for me here is that all of those systems are very different, but they have in common that they are well isolated from their environment in some way, and they are controlled, in their interactions, at least to some extent. And so the setup that we have in mind here is very different from the typical quantum matter solid state experiment, right? So in solid state physics, usually you have a solid and they have phonons, you have a heat bath somewhere. Here, the setup is very different, and we're really thinking of dynamics, right? So typically in cold atoms, you can prepare an initial state that would be maybe a product state, and you can really think of just unitary evolution from the Schrödinger equation, right? And this initial state will be, for me, like it will have some overlap with, it will be a high energy initial state. Its energy density could be very high, meaning it will overlap with eigenstates in the middle of the spectrum. So, so the physical system I'll have in mind is not a field theory. It will actually be a nice lattice model that has a bounded on-site Hilbert space. So typically, the many body spectrum will look like this cartoon, right? And we'll be thinking of states, initial states that again overlap with pretty much all states in the middle of the spectrum, all states in the spectrum. So if you remember your statistical physics course, it means that if your system thermalizes, it should really have infinite temperature in some way, right? So it will be at very high energy, okay? So I'm very far from any ground state physics, and we're very far from the ground state of the system, and there will be no relevance of what the ground state of the system that I consider is. And actually, for the examples I'm going to talk about, there's even no ground state. Okay. All right. So that's just a very broad introduction. So this talk in particular is going to be about entanglement dynamics. And so this slide I'm going to go very quickly because I think it's not useful for this audience. If you take a many-body quantum system interacting, and you just think about what entanglement does at long times, if you start from a product state, well, the generic expectation is that the system will thermalize if it's generic enough, and it will say you only have energy as a constant quantity. You will approach locally, even if your whole system is in a pure state. Locally, you'll thermalize at long times. You'll forget about your initial condition. Even though the dynamics is unitary, but locally, you only remember about conserved quantity, and so you have an emergent thermodynamics and hydrodynamics basically at long times. Okay, and so this tells you, of course, if you take a subsystem A, it will be highly entangled, volume law entangled at long times. Okay, so we've seen plots like this, I think, in many talks in this conference. Well, the typical behavior of entanglement in a many-body quantum system will be, okay, entanglement grows linearly with time and will saturate with volume law corresponding to thermalization. And here I'm showing just numerics in 1D for a typical non-integrable system of this behavior, right? So this is, if you take, say, a spin chain non-integrable, that's kind of what you expect, right? Entanglement grows linearly, and it saturates in 1D to something that scales with the size of your entanglement interval, okay? Okay, so that's the general rule, and it's interesting, and it has all of the physics of thermalization in it. In this talk, I'm actually going to try to break this. Okay, so like all general rules, it's interesting to find counterexamples. And so many of the, many people also in condensed matter in particular have been trying to think about ways that you can slow down entanglement growth in some way. So let me mention one example that I will not talk about in this talk, so that's the only slide I have on it. So one way to slow it down is with disorder. And that's a phenomenon known as many-body localization, which is close to my heart, but I'm not going to talk about this today. And so the claim is the following: if you just take a lattice system, so here I'm working in 1D, so say I have hopping fermions, but you put random, say, chemical potentials, okay? But you have interactions, so if this disorder, if the randomness is strong enough, you can have a regime in which your system will not thermalize. Okay, and the claim are like summarized below here in this talk. Like entanglement can grow very slowly, logarithmically as a function of time instead of linearly. And if you think of many-body eigenstates of a system, if you take a computer, you diagonalize this Hamiltonian. Okay, you can only do small systems, and you look at the entanglement of each eigenstate, even very deep in the spectrum, it obeys the area law, like a ground state. Okay, and so what it tells you is that the system doesn't obey the eigenstate thermalization hypothesis. I mean, meaning that each eigenstate, should obey, should have volume law scaling if you believe in thermalization. Those systems don't, and the basic intuition you should have is, excitations are localized here, even though you have interactions. And so the system cannot thermalize. So that's one example where like entanglement is different. But I'm going to talk about something quite different today. But I think it highlights the main point I want to make. So the thing I want to talk about today are dynamical transitions or eigenstate transitions where entanglement changes dramatically. Okay, so what I want to imagine is I have a parameter, I call it G, right? Where if I have a phase where G is small, where entanglement, here I'm thinking of 1D, behaves as in this plot. So it grows linearly. Okay, it's like a page curve, right? It grows linearly and it saturates to volume law, right? And it's this either random matrix or eigenstate thermalization behavior. But maybe as you crank up this parameter, you get a different behavior where entanglement will grow more slowly, maybe logarithmically, maybe it will just saturate to R yellow, right? The claim is that, so I'm going to call such transitions entanglement transitions. So in fact, I think we saw already some example in this conference of such entanglement transitions, for example, in those driven CFTs. Yesterday for me, or I guess this morning in Japan time. And those entanglement transitions, they can occur in dynamics. They can occur in eigenstates. They will not occur in the ground state of many body quantum systems, right? The ground state will satisfy the area law usually. They will not have such dramatic changes, but they can occur in the, you take a many body quantum system and you think of an eigenstate deep down at very high energy and ask if you can have a transition between area and volume law. Or maybe a bit more intuitively, you can think of dynamics again and have this behavior here and ask, okay, if I can have a transition and tune a parameter where we get a completely different type of entanglement scaling. Okay, and that's what I want to talk about. And I love phase transitions, and we like critical exponents and universality, and so I want to just illustrate two examples of such transitions that we have uncovered recently. And that have attracted a lot of attention. And I think there's a lot interesting going on for those transitions, including things we don't understand. So the first example, I want to talk about two examples. The main example I'm going to talk about is actually the more recent one. So it's not chronological order, but it's the one at least quantum matter physicists like better. Okay, but I will mention, so it's something that occurs in random quantum circuits. So it's called the measurement-induced transition or measurement-induced criticality. And so the idea is fairly simple and fairly intuitive. So hopefully I can explain it well in this slide, just qualitatively of what's going on, right? So this was introduced in those two papers, I should say, Skinner, Ruman, and Nahum, and Lee, Chen, and Fisher. And the basic idea is to come up with a model of dynamics that has some competition between scrambling or chaotic dynamics and physical measurements that will disentangle the system. Okay, so let me unwrap this a little bit. So those authors just modeled like chaotic dynamics or non-integrable dynamics in a way of taking of just a random unitary quantum circuit. So say you have a 1D system, so this is position, this is space. This is space, this is time. So you have this brick wall pattern. Each rectangle is a random unitary gate. Okay, it's random in space and random in time. So there's no energy conservation, nothing here. Okay, random unitary circuits are useful because we can do calculations. I'll come to this. But also you can think of them as kind of a generalization of random matrix theory in some way. Well, that's how I like to think about them, but because you put really the minimal ingredients, right? So here the minimal ingredients is you put locality, because the gates are, this brick wall pattern tells you have local interactions, and you put the unitarity of quantum mechanics, and that's it, right? But then you don't have any extra conservation law or anything else, okay? So a random circuit in itself has very chaotic dynamics. It's basically as chaotic as it could. Because of the hard gate, you forget your initial condition pretty much in one layer. And you can easily compute entanglement into a system and show that it grows linearly with time. If you want, it thermalizes to infinite temperature. Okay, so each here, I should say my on-site Hilbert space, you could think of it as a qubit or maybe a qubit, right? D-level system. Okay, so this, in this random unitary circuit, entanglement grows very quickly. So now you put another ingredient, you put local projective measurements. So each black dot with the probability P, you measure your qubits or qubits on that site. Okay, and when I say measure, I mean like measure as in quantum mechanics. That is, the outcome of the measurement is given by the usual rules of quantum mechanics, and the measurement is projective. That is, if you find your spin up, then your system is, you project onto that spin being up. So you can hopefully understand, like if P is 0, like you make no measurement, entanglement in the system grows a lot. But say P is 1, every single black dot you measure the state of the system here locally. So for example, you measure the first qubit, you find it's up, you measure the second qubit, you find it's up as well, you measure the third qubit, you find it's down, so on and so forth. But because the measurement is projective, if you measure everywhere, you just get a product state, right, after projecting. And so the entanglement entropy of your system is back to 0. Okay. And so what those authors argued, and they mostly studied this numerically, and I'll tell you how we understand this analytically now, is that as a function of P, you can really drive a transition in the system. So what's plotted here is numerics. So this is entanglement entropy for a fairly big system. So the way they access such systems is they use Clifford gates, which allows them to, they can be simulated classically, but that doesn't really, it doesn't really matter for P equals 0. So this is entanglement entropy if you wait a very long time in such a circuit. So that's like in a steady state. So that's entanglement entropy versus subsystem size. So if P equals 0, you see it grows. This is actually volume law. This is a log-log plot, but it's just linear here. And as you increase P, you see eventually entanglement just saturates. Okay, it doesn't scale with the size of your system anymore. And you have a transition in between, which they kind of like, okay, if you trust the finite size numerics, it's kind of this black curve here, which separates the behavior where entanglement grows and where it doesn't grow. Okay. So that's an example of such transition where you go from, again, volume law to area law, and you have this change in entanglement behavior. And so this problem has many interesting connections to quantum error correction in particular. You can think that the measurements are like external noise. It's the environment that's like measuring your system. You can think of them as errors. And this transition is basically a transition in how much information you can encode and recover from your quantum circuits. Okay. So this problem, I think those papers came out like maybe 2 years ago now, maybe a year and a half. So there's been many more papers on this and many variants, and this is just completely non-extensive lit. There's been like dozens and dozens and dozens of papers that came out of this. I'm going to talk about a theory of how we understand these, and what can we say without doing numerics, and how can we try to understand them. But people have come up with many variants. If you don't like quantum circuits, people took more realistic models. You still have a transition. You don't need a random circuit, right? You can put any physical Hamiltonian and also do measurements. So it's something fairly universal that occurs in quantum systems. If you don't like entanglements, which is probably not the case in the audience, people came up with other observables that maybe you can measure more easily. I'm going to talk about entanglement. And people came up with various variants of this transition. You can have different type of physical measurements where you take different operators that don't commute, and you can also drive different type of transitions depending on which operator you measure, for example. Okay. So that's the basic setup, and I'm going to talk about this quite a lot more of trying to understand, tell you what is going on here in this transition. Maybe I can just pause for 1 minute just to ask if the setup is clear. Okay. All right. So before I tell you about how we understand transition like this, let me mention another example, which actually came earlier, which has to do with random tensor networks. So this is a bit more abstract for condensed matter people, but hopefully for like this crowd, this will be an interesting example. It was actually, it came from, so the name of those tensor networks, they call holographic, and they were introduced in the context of, coming up with, I don't know if I want to say toy models, let's say for ADS CFT. Okay, and so they were, one of the key papers was the paper I'm quoting here, from Patrick Hayden and Collaborators in 2016. And so those holographic tensor network can also have those entanglement transitions. So let me briefly explain how this works here. So this is kind of a different setup. We don't have time. You have a tensor network. So each dot here is a tensor. Each leg is a contraction of a tensor. each node is a random tensor, right? So we take them to be Gaussian. So it's taken to be at random in some, any distribution you want. So why are they called holographic? Well, the physical degrees of freedom, so the physical legs live at the boundary. So like you see, you have dangling legs at the boundary of here. Like you have a circle and you have legs that come out. Those legs correspond to, say, your physical system. Okay, so effectively what I've drawn here is like a 1D wave function, right? That lives, the physical degrees of freedom are at the boundary. So you could have, say, a qubit. And so this is a wave function that's given by contracting this huge tensor. Okay. Essentially, you should think of it as a 1D wave function. Again, it lives at the boundary here of a random PEPS or tensor network. So PEPS is just the name of this particular type of tensor network. Again, each node is random. And we're fixing the bond dimension, that is the number of degrees of freedom, the dimension of the tensor on each leg is fixed, okay, and you can make it continuous. And so it was argued that if that bond dimension is large, this has some similarities with ADS-CFT in some ways, and entanglement, for example, is kind of given by minimal cuts through this tensor at large D. So it's a reminiscent of some of the Ryutake and Agi formula, for example. Okay, and so what we argued in that paper with Andrew Potter, Yi Zhuangyu, and Andreas Ludwig is that as a function of bond dimension, and you can think of its bond dimension, you can make it a continuous parameter. You can also drive transitions. Where if the bond dimension is small, like if you think of the entanglement of here, you consider entanglement of that boundary interval, right? So you have your 1D system and you ask about entanglement of this. Okay, so here there's no Hamiltonian, there's no time evolution, right? I'm just have a family of random wave functions. Okay, so it's really a, it's a toy model in that sense, right? We just give ourselves family of random, it's like putting, instead of doing page calculation, we just put more structure, right? So we give ourselves like a random wave function, a family of random wave function, and ask how entangled are those wave functions. And the claim is that if the bond dimension of those tensors is small, so in particular if it's 1, for example, you see you have a product state, you have 0 entanglement. But you can tune it continuously and you actually have a phase transition where like if you change D, it remains area low and then you have a transition and it becomes volume low. And eventually at large D, it has kind of a minimal cut through this tensor. Okay. So I'm mostly going to talk about the measurement problem, but those models actually, I mean, they don't look, they look kind of different, right? Those two things are introduced, but they're actually the same in the sense that they basically have the same theory and they're basically the same type of transitions. So it may not be obvious from here, but so coordinates matter people like the measurement setup a bit more, right? Because it sounds, it has, so I don't know, maybe a nicer physical interpretation. If you like tensor networks, this is kind of a nice example as well. All right, so in the time I have left, I basically want to tell you about this transition a bit more and why do we care and why is it interesting, right? So it has many nice features. And so originally it all came out from numerics, right? So those papers, so here I'm showing figures from this original paper, and this is numerics, right? So those authors, they studied, they took Rényi entropies and they changed P and they tried to do finite size scaling and understand this transition. And so what they found is that it looks like a nice second order phase transition for all the Rényi entropies. All Rényi entropies have this transition at the same point. And so as you see, this is a finite size collapse of entanglement minus entanglement at criticality and rescale in the way you would scale, normal second order phase transition. And so they find that there's a lot of universality. So it doesn't depend on many details of how you set up your circuits. You find critical exponents. For example, you have a critical correlation length exponent near 1.3. Interestingly, you have a dynamical exponent, so that relates space and time, that appears to be 1. And so I'll try to convince you it's correct. Even maybe more interesting, there appears to be conformal invariance in this problem. So even though like the setup in that measurement circuit, space and time are very different, right? Like space is a spatial thing and I apply my circuit and I do measurements. But the claim is this full 2D invariance, conformal invariance at the transition on those circuits. And to illustrate this, this is a plot of the mutual information. So you take, say, you have a system that's 1D with periodic boundary condition. You take two interval A and B with position x1, x2, x3. And numerically, they found that this quantity, just the mutual information, scales only with the cross ratio eta. Okay, eta is the usual cross ratio of conformal invariance, right? So it's x1, anyway, you know what the cross ratio is. It's this, so this is just a cross, it doesn't depend on x1, x2, x3, x4 independently, it only depends on this special ratio, which is, so it behaves like a, you know, a 4-point function in a normalized by 2-point function. So it has, you know, it looks like, it's usually a hallmark, right? So this did check this only spatially, but combined with z equals 1, this is something that really tells you you have conformal invariance here. Okay, and so that's purely numerical evidence so far. Okay, and again, it's pretty surprising, right? There's no low energy physics here. It's like highly, you know, just entanglement dynamics in those systems. But it appears to have a 2D CFT underlying this. Okay. Okay, so now I want to switch to like theory. So this was all background and giving you numerics and defining the problem. And probably that's the most important part. So now let me tell you how, you know, we try to think of it in a theory way, not doing numerics. So how can you analyze a transition like this, right? So again, it's not the usual phase transition. It's not like you can just think of symmetries and come up with a field theory for it. So it seems like a very hard nonlinear problem if you think about it. So what we need to do is we want to compute entanglement entropy. And, you know, we want to average over, say, the, you know, we have random hard gates. We have the measurements that occur randomly with a probability. So that's what I call measurement locations. And the measurements are also random because it's quantum mechanics, right? So if you measure a spin, it can be up or down with given probabilities, right? That depend on your wave function. So that's what I call measurement outcomes. So that's we want to compute, and I'm trying to phrase it a bit more like in equations here. So I'm going to think of a circuits, you know, so I have a given quantum circuits, I have hard gates, and I'm going to think of a given realization of those random hard gates. And I also have randomly with probability p some measurements, and here I put in red where I put a measurement. Right, so imagine that's a configuration of where I have my measurements. So I should say I'm thinking of the measurements in the so-called quantum trajectory picture. That is to say, I'm not thinking of mixed density matrices here. I always think of a pure state. So you have a wave function, it's a pure state. You make a measurement, and then you have, like, say you have a qubit. Again, the spin could be up or down. And you measure your system, say it's up. I'm saying, okay, I choose this path in the universe where that spin was up, and I still have a wave function where now this spin is up. Okay, so I have a pure state at all times. And so I can compute the entanglement entropy of that pure state. Okay, so I have those quantum trajectories with different measurement outcome. And again, like this red spin, for example, could be up, this other red spin could be down if you measure it, and so on. Usually when you think of measurements in quantum mechanics, you want to, you project, and then you want to normalize your wave function after that, right? Because it's not normalized anymore. Here, what I'm going to do is I won't normalize my wave function. I will only normalize it in the end when I compute entanglement. And so if you ask, okay, again, you measure that spin here to be up, this one to be down, this one to be up, and so on. And you ask, what is the probability that this happened in quantum mechanics? So it turns out it's actually precisely trace of rho. So I don't know if you've thought about measurements, it's probably obvious to you. For me, when I first thought about this problem, I had to convince myself. But you know, this is the so-called Born rule, right? So it's just like the probability in quantum mechanics to observe measurements. It depends on the wave function itself, you know, the norm of the measurement. So it's just trace of rho. And so the sum of all measurements outcome is obviously 1, you know, so those are all those probabilities. So what we want to compute in formulas is this. So we want to compute the average of the, so I'm writing Rényi entropy here. Okay. So this Rényi entropy is averaged over all those measurement outcomes. You have a trace of rho factor here, which tells you the probability to observe those measurements, right? So that's the physics of the measurements here. Notice that I have this divided by trace of rho in the entanglement entropy. That's Rényi entropy. That's just because rho is not normalized, right? So this normalizes the wave function when you compute entanglement. And then you want to average all of this over the circuits, that is to say, like the Haar gates and where I put my measurements. Okay. Okay, so that's a pretty hard problem. Like, okay, so like we just put it again in equations. That's kind of what we want to compute. And so it turns out that we can do a lot of it analytically, at least for those circuits. And for this, I'm going to use a replica trick. So we had lots of replica tricks in this conference as well. So, hopefully everything is familiar with this here. And the reason is we want to average a log, right? And I have a log of a ratio. So we're just going to replace the log by this usual formula. So notice that I have like two indices here. So n is the Rényi index, and m is this replica index that I introduce. Okay, and so of course I'm going to take m integer and then try to analytically continue as m be a real number. Okay. And so the main claim I want to make, and I'll try just to give you a flavor of it, is it turns out that actually averaging trace of rho to the n, everything to the m, where m is integer, is actually something we can do at least to some extent. And it's, okay, it can be mapped onto the partition function of a 2D classical stat-mech model. And so those stat-mech models, they've become pretty popular, I guess, in the field of quantum circuits, and many people are working with them now, and they can be used to show many interesting things about quantum circuits. The basic formula for this is also something we've heard before in this workshop. It has to do with Weingarten functions. And so it's kind of represented in cartoon here. You want to average, so you take multiple copies of your system, you have replicas, and you want to average over unitary gates. And this Weingarten calculus function tells you that you have different type of pairings, and they come with some weight. So it's basically like a Wick theorem, if you want, but it's constrained because unitaries have some structure. That is just the way I think about it. If you're averaging over a random tensor, you would basically have Gaussian contractions of the legs. But here, because it's a unitary matrix, you have more structure here. So importantly, you have this formula, which is represented in diagram, which is known as the Weingarten formula. So basically what it tells you is that if you take like multiple copies of unitaries and you want to average over that Haar gate, it's given by multiple contractions, which are labeled by permutations of those replicas. So here Q is, so SQ is the permutation group, and Q is the number of replicas I have. And number of replicas is n times m plus 1. So let me unpack this a bit. N is the Rényi index. M is my replica index, and plus 1 is actually because I have trace of rho in that formula. So you see like rho enters like many times, right? So it comes down, I have one copy here and I have rho a to the n, and then I do this replica trick, so I have plus m. So that's my number of replicas. So, okay, this is of course like more of a technical thing, but just to give you an idea of how we do the calculation. So we can, we have those replicas of circuits, and we can average over those unitary gates using this Weingarten calculus, which is well known, right? We didn't come up with this. And so you can, and you end up with sums of spins, which you can, we call them spins, right? Because they will come in our stat-mech model, and that are permutations. Okay, and those will give you some weights you don't need to worry about here. So the main claim is something like this in equation, that if you average, trace of rho to the Q, where Q is some number of replicas, and average over measurement outcomes, we can wrap this exactly. If Q is an integer, we can map this exactly onto something that looks like a 2D stat-mech model, where now, the spins of that stat-mech model are permutations. So if Q equals 2, this will be like an Ising model. But if Q is not 2, this is like a more complicated thing. And so the nice thing is that it gives you a very nice picture of what those transitions are. And so that's mostly what I want to communicate here. So this formula is exact, right? So I should say there's no approximation whatsoever, except we take Q to be an integer. And I should say, of course, we also don't know how to evaluate the right-hand side here, right? It's just an exact mapping, but 2D StatMech model can still be complicated, right? But easier than the original problem we started with. Okay, and so now you ask, all right, but like, we wanted to compute entanglement. So what is exactly entanglement here? So through that mapping, entanglement looks like something like this. It's some replica limits of a free energy difference. And this free energy difference, so the difference between Fa and F0 is only something that changes at the boundary of that StatMech model. So you can understand this intuitively in the following. So you have this circuit, you have space and time, and now you do this average exactly, and I said, oh, you get a StatMech model, and that StatMech model is 2D, and the degrees of freedom, they basically live on the unitaries, right? So each gate you see here, I'm going to have permutations that come out because of these formulas. So you have like a 2D StatMech model, it actually lives on an hexagonal lattice, but it doesn't really matter, that lives here. And entanglement is, okay, you time evolve and then you ask, I want entanglement of this region A. And if you do this calculation, you find that, okay, like the only difference is this, if you do like partition function where you have entanglement, you just have like a boundary twist if you want, or you have a different boundary condition along A. And so this gives this following picture that I hope will be somewhat appealing to some of you in the audience of how entanglement behaves. Yes, I see there's a question.
Sorry. So in that case, all Renyi entropies has the same value, like what we get for random tensor network?
No, they don't have all the same values. So yeah, it's a very good question. So they correspond to. So the statistical mechanics model is the same in the bulk, but they correspond to different boundary conditions. So you're thinking of the random tensor network at large D, where they all become the same, right? Is that what you're saying? Yeah. So in general, they're not. We think they're not. We think, for example, they will scale with different way at criticality.
Okay.
So in the StatMech model, if you want, it's the same model in the bulk, but it's a different boundary condition. And it doesn't matter at large D for random tensor networks, but near the transition, actually it does. They will correspond to different boundary operator in your CFT.
Okay, I see. Yeah, thank you.
Sure. Yeah. So, but all Renyi entropies will have the same transition. But they will have different behavior. So here I'm not distinguishing too much all Renyis for now, but the basic picture is this. And so this picture, I should say, is from a paper that came out at the same time, but they have a nicer picture there than us, so I stole their picture. So the picture is this. So this statistical, so the claim is, okay, you have this entanglement entropy in a random tensor network or in those measurement problem. Looks like a hard problem. You can map it onto a StatMech model. And so I should say, like for the StatMech models, they've been around for a while. In particular, they were there in that paper as well, right, for random tensor networks. So it's always the same type of ideas that come out. And here, like so the nice thing is that this gives you a very nice picture of what those transitions could be. So it turns out that P, like this measurement rate, or something like the bond dimension in tensor networks, it's basically something that drives the temperature of that StatMech model. So if P is small, the StatMech model is ordered, and it's ferromagnetic. And so here we're drawing as a cartoon, we're imagining it's an Ising model. Okay, in real life, it's not an Ising model. It's it has those permutations, but let's imagine I only have two replicas, so it's an Ising model. Entanglement is basically having a different boundary condition on that Ising model. So say all spins are fixed to be up, but on that entanglement region, your spins are forced to be down. Okay. And the claim is that entanglement is given by the free energy difference of inserting this domain wall. And now you ask, okay, what is the free energy cost to add a domain wall in, say, an Ising model in a ferromagnet? Well, it scales with the size of the domain wall, right? Because the model is ordered, so you have some string tension, And so if you make the interval very big, it costs more energy, right? Each bond here is unhappy. And so you have, this free energy cost is going to scale with LA. Okay, in particular, if you have a completely ordered StatMech model, you can also convince yourself this domain wall is going to take a minimal cut through your tensor or through your random circuit. So again, this is kind of reminiscent of a Ryu-Takayama formula, and in random tensor networks, it's what happens at large T, right? So you take a minimal cut through your system here. But here, if you want, we have a way to tune the quantumness here. Like as you tune P, right, you go away from this minimal cut. And eventually, as P goes through this transition, you get something very different. So if you want, your minimal cut or domain wall will start to fluctuate a lot as you change, this variable P. And then you get to this transition. And in this phase here, the StatMech model is paramagnetic. And now you ask, what does it cost to have a free energy domain wall in an Ising model if it's paramagnetic? And the answer is it doesn't scale with the size of the interval, right? Because paramagnet is already a domain wall condensate. So creating a domain wall, it's not going to scale with the size of the system. So you see, it gives you, so this is a basic fact about Ising model, right? So here I'm asking about free energy cost of having a domain wall in the boundary of an Ising model. But it basically tells you about this physics of this entanglement transition. So here you just go from here to there. Here the free energy or like this entanglement entropy scales linearly. You have volume law, here you have area law. Yeah. And so the nice thing of this is, of course, we know a lot about scaling of StatMech models, right? So we can say a lot here. And the claim is that those entanglement transitions, they are basically ordering transitions in 2D for the StatMech model, modulo this replica trick, which is the whole complication. Okay. So of course, again, I'm sweeping under the rug. I don't have an Ising model. I have a replica limit of a model that lives with permutations, right? So you can imagine it's a bit harder. But at least in terms of scaling, we can say a lot. So for example, the Rényi entropies, so this will answer the question here. The Rényi entropies at criticality, for example, they will scale, they correspond to, we know how this free energy cost behaves for a CFT, right? You take a CFT and you change boundary condition that corresponds to inserting a boundary condition changing operator in a CFT. And different Rényi entropies will correspond to different BCC operators. But for example, this immediately tells you the Rényi entropies will scale as log LA. So this log LA has nothing to do with the scaling of entanglement entropy in the ground state of a CFT. Okay, here it's a property of a boundary CFT if you want, right? So delta here is the scaling dimension corresponding to Rényi entropy. It depends on n. And for example, mutual information corresponds to a 4-point function here. And so that explains why you see conformal invariance in numerics. Okay, so yeah, one thing I should say is, of course, this transition here. So if it's an Ising model, it's a CFT, right? And so we believe if it's second order, it's a StatMech model, it will be described by a conformal field theory. So I'm almost out of time. So let me just briefly say one thing about, so far I didn't tell you anything about what the StatMech model is, right? I just said, oh, it's something we can compute it. It's usually very complicated and nasty. It has those Weingarten weights, and it's, it doesn't even have positive Boltzmann weights everywhere. So I should say it's not even something you want to call maybe a StatMech model. There is one regime in which it's very simple. If you take the on-site Hilbert space to be infinite, so if you take, I said I had Q dits, if you take D to infinity, then the StatMech model is extremely easy. Actually, I wrote it here, so you see I can write it in one line. So it's sum of the permutations, and then on each link, the Boltzmann weight is probability P to make a measurement. You have nothing, 1 minus P, you just have a Kronecker delta. So this is a Potts model for the StatMech people in the audience. So it's just something that, it's just a Kronecker delta weight. So it actually doesn't really care that I have permutations. The number of states is Q factorial, and you just have a Kronecker delta interaction. The nice thing about the Potts model is we know how to analytically continue it. So for example, the replica limit is Q goes to 1, and it's well known, and it's very easy to show that you get bond percolation here. Okay, so for example, the correlation length in that regime, it scales as -4, with that exponent 4/3. We can also compute all the Rényi entropies. Here, actually, they happen to scale all in the same way. And there's a coefficient 1/3. Okay. And so I'll just finish this talk with maybe a question that's maybe more field theory oriented. So one of the main challenges in this field is to try to understand what the transition is at finite Hilbert space dimension. We want to identify what CFT it is, right? So I gave you this picture here. I said, oh, it's a nice transition between those things. And so what we want is understand the critical behavior. So for infinite Hilbert space dimension, it's just percolation. But unfortunately, once you go away from this limit, we know it's something different. So this limit is very special. It has an enlarged symmetry. So you see here, like, because you have those conical delta weights, it has a permutation that's SQ factorial symmetry. And actually, if you have finite Hilbert space dimension, it has a smaller CFT. It's a smaller symmetry. So the picture we have is that, the conformal field theory we're after is a fixed point of percolation plus a relevant perturbation that we know. And I should say one thing that we know is that those CFTs, they have central charge 0. So CFT with central charge 0 are a bit nasty because they are non-unitary. They are known to be logarithmic, and they are very poorly understood even in 2D. So the reason we have central charge 0 is because the partition function is trivial in the replica limit. Okay, our partition, so it's the case for percolation as well, right? So our partition functions, they're basically this, average of this, and in the replica limit, the partition function is 1. Okay, so the partition functions are trivial, but the criticality is still non-trivial. So we've tried, to write down field theories, and that looks like something horrible, like something I've written here. So it's kind of a perturbed parts, but there's a replica index, and we have no idea what the infinite fixed point is. And so I should say, like, CFTs with central charge 0, again, there are many famous problems in 2D that quantum Hall plateau transitions and so on. And actually, I did my PhD on them, and yeah, there's very little we know about such CFTs. All right, so again, it's getting late in Japan, so I'm just going to conclude and leave time for questions. Okay, hopefully I've convinced you that there's a new class of entanglement transitions, and I'm not claiming those are unique. We can find other examples, but we're barely starting to understand them on the StatMech, on the Kronos matter side. For some of those transitions on random quantum circuits and random tensor networks, there's an exact mapping onto StatMech models, and it's particularly nice for to get some analytic handle on those transitions. We're hoping to get an analytic handle on the field theory of the transition. Sorry, but we don't, except in special limits like infinite. This is like a large n limit, if you want. Where we can solve it exactly, we have no idea what the transition is, and and the main reason is that those CFTs or logarithmic CFTs with central charge 0 are pretty complicated. So there's still a lot to do. We're trying to classify those like we like to do in usual phase transitions. Of course, we want to understand the universality class and come up with maybe things you could actually realize in experiments here for those transitions, and like maybe more physical observables other than entanglement. But I think even conceptually, there's a lot to say about what those transitions have, whether there's anything really special about the criticality in those transitions here. And so with this, let me thank everyone for your attention. Thank you again, the organizers, for putting together all of this, and I can take questions. Thank you.
Okay, thank you very much for very curious talk. So is there any question? Takayanagi-san, please.
Thank you very much for very interesting talk about this entanglement transition. And I have a question about, I have two questions. First about criticality. So in the first part of your talk, you also mentioned critical behavior. And in the final part, you also mentioned the C equals 0, like CFT. Yeah. So are they the same, or do you have in mind different CFT?
No, yeah. So yeah, the criticality is controlled by this C equals 0 CFT.
That's always C equals 0.
It's always C equals 0.
I see. So do you have any idea how to identify this field theory description of this? Like maybe, I don't know, like maybe using ghosts or such a...
Yeah, very good. I mean, like I said, there's one regime where we know what it is, right? So like in this regime where you have infinite on-site Hilbert space for the measurement problem. So, you take this random circuits, but on-site you take a Q depth and you take Q to infinity. So it's like, large N for like, like I said, it's kind of like large N. Then the CFT is percolation. And percolation as a field theory is actually fairly non-trivial. It's bond percolation where you put a square lattice probability P to have a bond. So as a field theory, it's pretty, because it's kind of non-local, it's actually a C equals 0 CFT itself. You can convince yourself in percolation the partition function is trivial. But so
something similar to this loop gas-like model.
Say that again. Which model?
Is that looks maybe similar to loop gas model?
Loop gas, yeah, yes, absolutely, yes. So those can be mapped onto loop models, yeah. So the thing is that C equals 0 is not exactly constraining. They are like infinity C equals 0 CFTs because they are non-unitary, right? So there's no unitarity, there's no minimal model here. They are non-rational. Like at least like the one we're after is probably a non-rational CFT. So it doesn't constrain what CFT it could be. So there are many. Yeah, central charge 0 is probably one of the worst class of CFTs in some ways. So most likely, the transition we're after is non-rational. It has infinitely many primaries, maybe a continuum of primary operators. So central charge 0 tells you something, but it's fairly hard. So except in that regime where you have percolation, and percolation we know.
I see. Also, thank you very much. And one more question about this, your relation to also random tensor network, which is very interesting. And so usually, for example, in ADS-CFT case, we have some hyperbolic like tiling, we are assuming. But is this kind of transition is, do you assume some particular tensor network or is
no, very good. Yeah, no, thanks. That's a very good question. So I kind of swept this under the rug. I took a regular lattice. I took like a square lattice. Actually, not something that necessarily looks like a picture. Yeah, let's say square or triangular, whatever you want. But I took like a 2D nice lattice. It's an open question, I think, to solve those StatMech models on more hyperbolic geometries or something more interesting and think about the transition there. But you're right, like the CFT I talked about is if I assume the random tensor network is on a regular 2D planar graph.
I see. But do you expect that, that is universal? Or
I don't know, it's a good question. So one thing that we did in our paper is also we also did them on random graphs. We took random we took like fluctuating lattices also.
I see.
So this is like coupling the CFT to 2D quantum gravity.
Gravity, I see. That case also you have this transition.
And you get something different there. But we haven't done this, and that would be interesting, right? So one thing I mentioned, we did trees as well, for example. So that's the one slide I skipped actually. We also did trees. Like something that looks like, so it's not hyperbolic, but now it looks like a tree. And here, it also has some criticality and you also get like a different behavior, but it has, so to do something more hyperbolic, I think would be very interesting. And I don't know how to solve such StatMech models.
I see. Thank you very much.
Okay, next question. Numasa-san, please.
Thank you for the nice talk. And I have two questions. And so first question is, is this measurement-induced phase transition, is randomness important in this context? Or maybe my question is, is it self-averaging or not?
Yeah, it's a very good question. So the randomness is not too important. At least the randomness of the gates, for example, is not crucial. I mean, it's very important for me to do a calculation. Like the StatMech model I showed, I need this just because it simplifies life a lot. But people did numerics on, for example, so this was done with, you take the gates to be the trotterization of a Bose-Hubbard model where they truncated the number of atoms on site. So they took more realistic models. So now the gates are not random. And you still get the transition, still with the same exponents.
I see. I see.
At least that's fine. So you can
For
take all the
example,
gains to be the same. It's just harder on the theory side.
I see. I see. So for some solvability, so you take that. I see. I see. And another question. So you mentioned that so we can map the computation of linear entropy to the computation of some boundary change condition changing operator. So is there also some we can in this statistical model side we can also consider some bulk 2-point function or some bulk domain. So is there some meaning some interpretation in this quantum circuit side?
Yeah, no, it's an excellent question. Yes, there is, and people have asked this. So, you can ask about like Michael Gollins and David Hughes came up with this, for example. Like you can ask, you can maybe put an ancilla qubit somewhere in your circuit that couple and like put it in a bulk. And ask about its entanglement property. Maybe it's easier actually in the random tensor network. So here you see I put legs at the boundary. You can maybe take one of the tensors in the bulk and now couple it to a physical degree of freedom. So like a PEPS, you put an external leg and you put an actual qubit or qubits in the middle. And now, it's a way to probe the bulk, right? So you can do this, you can imagine that a tensor in the middle is coupled to a physical degree of freedom. And now you ask about the entanglement property of this extra degree of freedom you put in the bulk. And so this will couple to bulk critical exponents. And so, for example, people measured the magnetization exponent, if you want, or the order parameter exponent of this transition. So exactly as you suggested, basically, so we can do this. It's still fairly preliminary, but we can put bulk stuff if you want here and also probe it. Yeah.
I see. And is it, I just want to confirm, so is it also, so in the bulk side, so can we also confirm that so that have some central charge C equals 0?
Yeah, so it is still a C equals 0 CFT, but so we're trying a lot right now to understand more the criticality. We tried a lot on the theory side, but I should say again, it falls in the category. There are problems like this in Condensed matter of 2D C equals 0 CFT that people have never managed to solve. Right? So those can be like those can be very hard. But yeah, we're trying at least on the numeric side to understand what is the spectrum of that CFT, and also understand the bulk operators and so on, and get some kind of more information about the operator contents also of the bulk. And so we're actually doing this mostly on the numerics side to try to see how it differs from percolation.
I see. Yeah, interesting. Yeah, thank you very much.
Yeah, thanks.
Okay, is there any other question or comment? No, so if not, let's thank all the speakers in this conference again. So thank you very much.
Yeah, and well,
so before also
organizers.
Yeah. Thank you very much. And before we close this workshop, so we'd like to also thank all speakers and also all participants for this wonderful meeting and very stimulating discussion. Thank you very much. So we would like to keep this interdisciplinary activity ongoing. And next time we hope we have some all of you in Kyoto physically. So thank you very much.
Okay.